In this example, we're given some information about a kangaroo farm. We begin with 75 kangaroos, and then after 4 weeks, it's grown to 111 kangaroos. All right, so our goal is to write a continuous growth function that models this population over time. And to do this, we are not given a growth rate, so we need to solve for that to start out. So you can see that it's the continuous growth model. So what I've done is I've gone ahead and written out the continuously compounded interest formula or continuous growth model here, where A of t is the accumulated amount. It's kind of like what you end up with. P is the principal when we're talking about banking problems. It's the starting amount. E is the number raised to the rate times time. Now our rate is going to be as a decimal at some point here. We can get an exact rate and then convert it over to a decimal. For our purposes, I think that'll be fine. So initially, let's list out our variables and see what can we plug in that's going to connect all of these together. All right, so we start out with 75 kangaroos. We begin with 75, so that's going to go in for P. And then we're given this other specific information that after 4 weeks, it's grown to 111 kangaroos. So after 4 weeks, that's our time frame here, it has accumulated 111 or grown up to 111. We don't know what our rate is. So let's plug in the information we do know and then try to solve down for our rate. So we have 111 equals 75 e raised to the r times 4 power. So our time is going to be in weeks because it was 4 weeks given to us. All right, now we need to solve for r, but it's up in the exponent. That makes this an exponential equation. So the first thing we want to do is isolate the exponential part, the e to the power in this case. That exponent is not attached to 75, so we're going to have to divide by 75 to move that to the other side. So now we have 111 divided by 75 equals e raised to the r times 4 power. To get r out of the exponent, we'd like to get a logarithm involved. And because our base is e, let's apply a natural log to both sides. So natural log of 111 divided by 75 equals the natural log of e raised to the r times 4 power. Now, because we use natural log, that's log base e, it's the inverse of e raised to a power, an exponential function. So we're going to get very nice canceling out on the right-hand side and just be left with our exponent. So natural log of 111 divided by 75 equals r times 4. The last thing to do to get r all by itself is get rid of the 4 by dividing both sides by 4. So our rate is exactly natural log of 111 divided by 75 divided by 4. But for our purposes, we should be able to get a decimal, so 0.09801. As you're working out finding this rate, you would either need to keep a lot of decimal places, such as what I did, or keep the exact rate, that natural log, intact. For our purposes, though, I think we'll be okay with keeping the decimal. All right, so plugging this back in, we have a of t equals, we're still going to start with 75, e raised to the 0.09801 times t, t being the number of weeks, and that's going to be our model. Thus concluding part A. Now, according to our model, what's this population going to be after 11 weeks? Well, 11 is going to be a value for our time. And notice our time was in weeks because it was 4 weeks that we started with. So we just plug that into our model. A of 11 equals 75 e raised to the 0.09801 multiplied by 11. Okay, punching that into our calculator, rounding to the nearest kangaroo, we have 220 kangaroos after 11 weeks. Then we have one more follow-up question. How long is it going to take until the population reaches 400 kangaroos? Lots of kangaroos. All right, so that's an accumulated amount. A of t has been given to us to be 400. So we're going to plug this in to our original model we came up with in part A. So we have 400 equals 75 e raised to the 0.09801 times t. That creates another exponential equation. So solving this down, pretty similar to what we did in part A, we want to isolate the exponential part. So we'll divide both sides by 75. That'll be e raised to the power on the right-hand side. Just copying that back down. On the left-hand side, we could reduce this down. I think both multiples of 25. So this could be 16 thirds, or you could leave it as 400 over 75, as eventually we're going to have to get our calculators out. All right, next we have e to a power. So again, we want to use natural log is going to be the most efficient way to get through this. And using the natural log, because we have e as the base on the right-hand side, we're going to get that nice canceling out where we're only left with the exponent. So 0.09801 multiplied by t, and then we'll divide both sides to get rid of that decimal, 0.09801. That'll put t on the right-hand side all by itself. And getting this into our calculator, it is going to be natural log of 16 thirds divided by 0.09801. It's going to be approximately 17.08. So we can say that's between the 17th and the 18th week. All right, hope this helps out on modeling this type of problem, population growth. In this case, our population was increasing as we went over the years. Just based on the information, it could be decreasing over time as well. Just use the information that's given to you and model it appropriately. Good luck to you.